if we do proper reliability analysis, we need to consider the whole life cycle. So it's so easy to kind of focus your view only on the operational phase. So you are just thinking that, okay, what the product sees during operation, which kind of temperatures, humidity, impurities, vibrations, whatever is in the operational conditions. But sometimes these so-called pre-operational phases, meaning assembly processes, testing processes, storage and transportation, they might have really high stresses. Not, of course, the duration or number of cycles is typically quite small, but the conditions might be really harsh. And my example last time was coming from the assembly process, so that, for example, our electronic products typically never see as high temperature as they see during the manufacturing. During the soldering processes, the temperature with these lead-free solders, it must increase close to 250 degrees centigrade. And even our, let's say, power electronic components or high temperature components in general typically don't see that high temperatures. The operating temperatures might go quite close to 200 nowadays when you include the environmental temperature as well as the power losses, so internal stresses, but still not up to 250. It might sound quite small difference, 200 versus 250, but at least for some materials, it's really critical. So for example, our organic materials, our printed wiring boards, molding compounds, and these, we will come back to this issue again later on, that how their material properties are changing as a function of temperature. Okay, so these were basically the two main points from the last lecture, and then as I said, I kind of ran out of time, so I wanted to state a few words on lifetime analysis, or what kind of tools or models we have. And now I'm speaking very generic, so because we are coming back to these issues later on when we talk about specific stresses and testing and the correlation between the test results and field lifetime, so these acceleration factors. But anyway, what I want to say that as we have huge amount of different types of environment, then of course we need different types of models. So that's one of the, let's say, maybe even a drawback in reliability engineering, that we have too many models. We have too many equations, because we don't have this kind of theory, as I said last time. We don't have a similar type of Maxwell equations in reliability, where we could basically calculate all possible things. If we know the boundary conditions, then we could calculate something, because there are too many variables or factors affecting the reliability. So every model is based on specific assumptions, and therefore they are applicable only to certain situations. So, for example, typically the model is working in a certain temperature range. So, because it is concentrated on one failure mechanism, and therefore the mechanism is valid in certain stress conditions. And therefore, if you exceed, for example, those stresses, like go to higher temperatures or go to higher mechanical loads or something like that, then the model is not valid anymore. Anyway, as most of the events which we observe in our nature, they are more or less thermally activated. So we know that our sugar is dissolving into the coffee better when the coffee is hot rather than cold. We know that if we do a chemical reaction, it is happening faster if we increase the temperature, and so on. So this means that the event is thermally activated, and therefore most of our models, they contain a term which is stating how temperature affects on this specific mechanism. And this was originally developed or formulated by Swedish physicist Svante Arrhenius, and therefore we are calling these equations Arrhenius type equations. So it means that our failure rate or whatever is in the equation contains this kind of a term, x delta E divided by kT. So here we have just temperature, absolute temperature in kelvins. This is constant, Boltzmann constant, and this is the activation energy. So this activation energy tells us how strong is the effect of temperature. Maybe this next picture, even this is slightly confusing, but maybe this clarifies the situation. So here we have different curves representing different activation energy. So the activation energy is smallest here, 0.3 electron volts, and it is highest here, 1.2 electron volts. And in the y-axis we have failure rate. So we could also consider it as a reaction rate or whatever rate, how fast things are happening. And in the x-axis we have the temperature, so that the low temperature is here. So what this means is that if we start, for example, here, we have something in the room, temperature 25 degrees centigrade, and the activation energy is 0.3. It means that when you start increasing your temperature, let's say from room temperature up to 100 degrees centigrade, then your reaction rate or the rate of this event is increased maybe 1 order of magnitude. So from here, because the mean time between failures is decreasing 10 times. So from, let's say, 200 to 20 or something like that. But if you have higher activation energy, like 0.7, we are here, and then you do the same thing, that you increase the temperature from 25 up to 100, then you see that we already have, let's say, 1 order of magnitude from here to here, another order of magnitude from here to here, and third order of magnitude here to here. So basically, then the something is happening 1,000 times faster if you increase the temperature from 25 to 100. So this just highlights the importance of temperature in reliability engineering. So this is something that we come back. So basically, we are spending at least 1 hour or maybe even close to 1 whole lecture thinking about how temperature affects on the reliability. So that will be kind of the last part of this first part of the course. Okay, and then so already we can say that temperature has huge effect on reliability, whatever reliability or failures we are talking about. There are only very, very few failures which are completely temperature independent. And then when we have different type of stresses, but also different types of materials, packages, manufacturing processes, or whatever, then you need to start adding different parameters. So here is just one very, let's say, not that nice model, because we have here the temperature part, and then the reliability or whatever is here is a function of some non-thermal stresses. So here, these you could consider that these could be something to do with the electrical stresses or mechanical stresses or whatever. So this is just a function which could be coming from the actual physics. So it's based on really how this, let's say, electron flux is affecting on that specific failure, or it can be just statistical models. So we just do tests, and then we fit our results into the model and think that, okay, now it describes the effect of this stress. So therefore, we can kind of divide our models into 2 different types. We have so-called analytical models, and we have physics of failure models. So of course, physics of failure models are, in that sense, much more useful that they really, because the models are coming from the actual physical phenomena, then they might be more accurate. But the problem typically is that these become much more complex. So in practice, they are not that easy to utilize. And then we have analytical models, which can be, for example, empirical models. So we have just observed that, okay, this failure, mechanical tensile stress effects like this, and then we make a mathematical model, like put a polynomial or whatever there, and then we can solve it. Or it can be statistical model. So we are doing testing, and then we see that we change that parameter, like again, the tensile stress, and then we see that statistically this stress has this kind of a effect on the strength or reliability, and then we form a statistical model. So these are quite often much easier to use, therefore they are much more common, but the problem is that they might be completely misleading in those, let's say, outside of the boundary conditions where they are valid. So the model may describe the reliability or failure correctly inside certain boundary conditions. So when the, let's say again, the mechanical tensile stress is between certain values, but when you exceed it, then the failure mechanism changes, and then it can give you completely wrong results. So this is kind of to conclude, if we would like to have a reliability model, what it should have. So this is now the wish list for the model. Results are repeatable. Of course, that is quite obvious that if I'm doing the calculation, then the results should be the same as you are doing the calculation. If I'm doing the calculation today, or if I'm doing the calculation next week, I should get the same outcome. So when we are talking about mathematical models, then typically this is okay. The second bullet, which I have highlighted here, is it allows the use of accelerated tests. So here we come back to the issue which I already mentioned, that this model should allow the use of higher stresses or stresses outside the normal operational conditions. So for example, it is valid if we increase the temperature. So it should be able to describe the behavior of the product or whatever we are testing also during higher stresses, during under higher temperatures and so on. And if it does that, then it also maybe helps in the next bullet, which is to minimize the amount of tests. And this is also coming to the fact that if you have several different stresses, then if the several stresses have some cumulative effects or some interlinked effects, then if the model can describe these correlations, then you might minimize the amount of tests by, for example, using several different parameters at the same time. So it should basically consider the parameters and the interaction between different parameters. In the next slide, I have an example on that I'm coming back. I'll try to clarify this issue with the next slide. And then, of course, this should be able to describe the reliability behavior throughout the lifetime in all environments. So if this is more on concurrent stresses, this may be more on consecutive stresses. So for example, that if some events, some stresses are higher during winter time, and then you have some other stresses during summertime. So what is the combined effect of those consecutive events? maybe we are not including here the global warming or something like that. I mean that now we cannot predict what is the average temperature in 40 years or 50 years. Maybe we can have a rough guess that maybe it's 2 degrees on average higher or something like that. Let's hope it's less. But anyway, so here it's more point is to understand the let's say if something is happening during manufacturing or storage, how does it affect also during lifetime, or if there are some different types of stress conditions during the lifetime, how that could affect on the reliability. That could be, let's say, very application-specific things. If you are thinking about something, let's say, an autonomous vehicle going into the mines, so here, there, in the down there underground, the temperatures might be quite high. The humidity would be quite high. So it's operating there, let's say, the daytime, and then it's stopped during the nighttime, which most probably then it's out of the mine itself, and there maybe there's let's say temperatures which are below 0 or something like that, so there could be a condensation and these kind of effects. So this is what is meant with the last bullet. So I wanted to finalize this part with by giving an example on this, what are the challenges related to this kind of combined loading conditions. So an example which we are coming again back later on. Sorry, I always need to or maybe too frequently I refer to something which is coming during these lectures, but as we cannot cover everything with a single lecture, so when we are talking about accelerated life testing, we will come back to these things, that what is happening and what are the challenges and what are the advantages when using several stresses simultaneously. So let's see, I hope that we will get a nice case example from ABB on that lecture. Let's see if that is going to be realized. This is this example, what you see here is coming from our own research a few years back. Here is also, let's say, power package. So this is an Infineon power package component. And at that time, we were interested in combined loading conditions. So in fact, what we have here, you see the test setup. So we have a vibration shaker here, and then we have stacked DC boards. And the stacking is only that we can have more samples tested simultaneously. And then this actual component is mounted here. So we have every printed wiring board has 4 components at the center of the printed wiring board. Why only here is, of course, because of the bending amplitude. So we can assume that when this board starts to vibrate up and down, then the center row, we can kind of consider these 3 components quite equal. And here, what we have is vibration together with thermal power cycling. So basically, here you see the one power cycle. So what we do is we put the power on, which means that this component heats up. So this is the heating curve, and after 15 minutes, it has kind of reached the maximum temperature. Here we have the thermal camera image from the top. So the temperature, maximum temperature is somewhere in the close to 125 degrees centigrade. And then we let it cool down for 15 minutes. So 1 cycle equals half an hour. So you can hear the scale bar. So it's roughly 125 at the center of the component surface. So this is kind of a constant stress. So we do this power cycling. And then in this little bit strange looking diagram in y-axis here, we have the component strain, meaning that you can consider that this value as how much vibration power is given to this board, so how much this part is moving upwards and downwards, so how much these boards are bending up and down. So this is 0.1%, meaning that very small strain at the surface of the board, and this is 1% strain. So meaning in one cycle, this upper surface is stretched 1%. So basically, locally, the length is going from 1 millimeter to 1.01 millimeter. So that is just the y-axis. So if we think just pure vibration, so this is the blue dots are experimental points, and the blue curve is the experimental fit. So while increasing the bending amplitude, increasing the strain in the board, you decrease the lifetime, which is here as a function following this blue curve. So when you are close to this 1% strain, then you need only very small testing time. So this is 0.1 hour. So maybe 6 minutes, I think. So here we are talking about 1 minute or even less. So it's immediately when you put the things on, these components fail when you have really high strain. And then when you start decreasing the strain, then the reliability follows this curve. So these data points here, we are talking about hundreds or 1,000 hours, so few weeks is here. Then if we put constant power, let's take that we have now this kind of a reasonable strain producing certain type of failure mode, and then we, instead of putting cyclic power, we put constant power. So meaning that basically these components are all the time having this 125 temperature. Then we can see that what is the acceleration. So let's pick a point, for example, from here and here. So you can see that with this 0.4 strain, we would be from, without the power, it would be 200 hours the failure time, and with the power, it would be something like 30 hours. So this is the acceleration. But if we start cycling, so we put the power on and let it cool down, which if one considers only the effect of temperature, then one might think that, okay, we should have better reliability when the temperature is not all the time on. But actually what we see is the red curve, so it even speeds up the failure because it accumulates the stresses. So we have mechanical stresses coming from the vibration, and then we have thermomechanical stresses coming from the power cycling, so different coefficient of thermal expansion of the materials. So now you have even higher acceleration. So now you think that, okay, we have 3 curves. The problem is that if we think about as a function of vibration loading, we have different acceleration factor. So here, when the vibration loading is high, then it dominates. So adding constant or cyclic power does not basically change the reliability at all. But when we are decreasing the vibration loading, then the power cycling or power losses and power cycling kind of increase their effect. So now, if you would like to make a model, reliability model, that would be relatively complex because you would need to include also the y-axis. So you don't just have the acceleration factor, which is basically the difference in the x-axis, because it's also a function of y-axis. Hopefully you got my point here. So it means that, for example, this point here represents the failure time, something like 2000 hours, which is 4000 cycles, if you have zero vibration loading, zero mechanical loading, just power cycling. Okay, maybe I spent even too much time on this, but hopefully you got the point, the challenge on kind of making really a proper lifetime model or reliability model under these kind of combined loading conditions. Of course, if you are clever enough in mathematics, that's not a problem to get a correlation between these three curves. So that's not a problem. But is it really, does the model have really the physical meaning behind? So then if we change something, we have another component type, different type materials, different dimensions or whatever, is this model, which is basically based only on mathematics, still valid or not? You need to, of course, at least test it and then see if it's valid or not. So that's the describes the usefulness of a proper reliability model. Okay, so let's go into the actual questions for today. So basically, this should end up in the understanding of what is the stress versus strength approach. So the critical question is why failures occur, where the products are failing, and then finally, if we are able to answer these first two questions, then maybe we are also able to answer the third question, when the failures occur. So of course, this is the question what the reliability engineer mainly wants to or needs to answer. So your manager wants to know that, okay, what can we promise to our customer when the wear out starts or whatever. Okay, so as was already mentioned last time, basically all products, whatever product we are talking about, they are failing sooner or later. And the actual time when the failure occurs is dependent on several different things. It is dependent on the product design. It is dependent on the materials what we have used. It is dependent on the manufacturing defects. It is especially dependent on the operational environment and different types of stresses which the system sees in the operational environment. But we can affect on the occurrence of the failures by affecting on these things if we understand these properly. And of course, the problem is that quite often there are several failure mechanisms which are occurring at the same time, and they might have cumulative effects, or one specific mechanism might dominate at certain times or certain phase in the life cycle or under certain stresses, for example. Meaning that there could be simultaneously, let's say, electromigration, which is driven by the high electron flux. There could be electrochemical migration, which is driven by the humidity and impurities. There could be, for example, fatigue, which is defined by the, let's say, vibration loading. And all these are happening at the same time, but it might be that only one of those really define the reliability because that's the dominating mechanism. So here is just a slide for a generic idea, why do products fail? And maybe here we want to blame the customer. So everything is kind of coming back to the new things which we want to include into the, let's say now maybe we are more talking about products. So let's narrow our vision and think about some electronic product. And then we have a customer who wants something, some functionalities from the product. Let's say that now, coming back again to this boring example of mobile phones, so foldable display. So at least phone manufacturer Samsung is thinking that the customer wants a foldable display. So that's the technology trend. And then based on that technology trend that you need to have a foldable display, you need to have a certain design. So how you design the phone that it can have the foldable display, and this design then defines what kind of materials and components you need to use. So the display itself, but also how this folding mechanism is made, what kind of materials is used for that, what kind of components is used for controlling the system, and so on. And then based on the design, there's the material selection, and based on the material selection, you have the manufacturing process, because you need to use certain type of processes in order to manufacture, let's say, assemble certain types of components. And then from the customer requirements, as well as from all these, there comes the requirements for the testing. So for example, test coverage, do you need to test all the components? Is it enough to test only the whole end product? Do you need to screen all the products, or is it enough that if you check every 100 product which is coming from the manufacturing line, and all these things? So basically, all the decisions which are made here are more or less coming back to the chain, either this way or this way, and they are affecting on design, materials, manufacturing, and testing. That is just the point of this slide, which might be self-evident, but it is really important to understand that. Here is another slide. This is extremely old, but still want to kind of just highlight. Don't pay attention to any of these numbers here, but the point here is that there are different types of defects or failures, and here the largest part or fraction of failures is caused by the parts. So in electronic product, maybe we could say that these are the components, including also not only the, let's say, classical electronic components like ICs or capacitors or resistors, but also the other parts like the mechanics, like the printed wiring board, the display, the sensing components like accelerometers or whatever. So any part. Then this no defect here means no defect found. So NTF or NTT, no trouble found. So meaning that when the product was sent back, then nobody could really find out what was the primary reason behind. And this is surprisingly common. And this is also something that we will come back into the testing part. So can our testing somehow help in finding the root cause also for this? Then there's manufacturing induced failure. So some, let's say, quality related things. Induced, that means the usage, it could be misuse. For example, you are hitting your phone with a hammer, then maybe that's not a problem from the manufacturer point of view because that's a clear misuse. And then the challenge is, of course, where the borders are drawn. So what kind of environmental conditions your product is you can use it and what not. That's the big question. Design related things. Then here is wear out. So the product getting old. Software related problems. So this is basically something that we completely exclude from this course. And system management maybe also. So these parts here is kind of things that we don't include. So we are here in this course more focused on the hardware side rather than software bugs, because I don't have any knowledge on that area. Okay, so let's jump into this stress versus strength approach. And here I also added this load. Even the definition which was discussed last time is that the stress is kind of the extent of the load. But here I would like to emphasize that now the stress is not only mechanical stress. It can be whatever load and how high or low that load is, that is our stress. So for example, what is the maximum temperature or maximum humidity or maximum bending radius or whatever. And then we have a certain strength. So how much the product, material or device or whatever can withstand this specific stress or load. So a product is a function of the design strength, meaning that if you design something that it will be used in higher stresses than it is targeted to, so the stress exceeds the strength, then there's a high probability of failure. Meaning that if you have a pen, I'm not sure if you can see this, but this is designed so that it can withstand small amount of bending. But if I would do, I don't demonstrate it now, but if I would use a little bit more force, then of course this pen would break, because I am using higher stress than what is this pen's strength against this kind of bending load. So simple as that. And then of course, when we are talking about products which are components of several different things, then every component has its own strength, and then the strength of the whole product is some kind of a function of the strength of the individual building blocks. So you can approach this with two different ways. You can if we talk about, for example, mechanical strength, then quite often you can approach it from the weakest link thinking. That if you have a chain and then you apply a stress, then the chain breaks when the stress is increasing the strength of the weakest link. So that is one thing. But then if you think about, let's say, for example, electrical stresses or some thermal stresses, and then you have huge amount of electronic components, your system, then it might be that you have this kind of a cumulative effect, that every component is affected by the temperature, and then the cumulative effect is not that one component burns, but the system is not functioning anymore. So it's a cumulative effect of all building blocks, which then we are coming back to this, let's say, military type handbook type of approach, that the more complex your system becomes, then the reliability is decreased. The other thing what we need to understand is that when we are talking about strength, then it's not for one specific component, it might be one specific value. So for example, let's take an example of ceramic capacitor. So how high voltage it can withstand. For one capacitor, we of course can measure it. We increase the voltage, and then after a certain value, we have an avalanche effect, and then the capacitor burns. And then we could state that, okay, this capacitor withstanded 963 volts before it burned. But if we take the next capacitor, the value may not be exactly the same, because it is ultimately defined, this strength against voltage is defined with the imperfections which the, let's say, the insulating material between the capacitor plates has. So what kind of defect it has. So then if we take, let's say, 10,000 of these capacitors, we have certain type of statistical distribution. It can be very wide distribution when if our process produces large distribution. So maybe the process control is not that good. It can be very narrow distribution if our process is very nicely in control. So for example, all the dimensions when we are, let's say, doing the manufacturing of that capacitor by thick film screen printing and so such things. So how well everything is in control defines what is the width of the distribution. So therefore, we need to consider also that there's some statistical distribution in the strength, as well as there is, of course, a statistical distribution in the stress, because the stress might be different depending on which kind of use application you have, even which kind of user there is for that specific application. So this might be, or this definitely is very simple thing, but it's still good to understand that if we think about failure, so this hatched area here indicates the failure. So this red curve is the stress distribution, and the blue curve is the strength distribution. And when stress increases the stress, when stress increases the stress, then you have a higher probability of failure. Sometimes, of course, it's an immediate failure. For example, in the mechanical thing, so when the stress is high enough, then definitely this fails. For some other stresses like temperature, it might be slightly more difficult to kind of state what is the absolute threshold. So how you can affect on this, the probability of a failure, is either putting your stresses lower. Let's say you use active cooling, decrease the temperature, get the average temperature lower. You make your product stronger, so by moving this one upwards, using a technique, new material or something which makes your part more strong, or then you narrow this distribution. So you move this part and this part closer to the center. So also that decreases this area here. So one can kind of say that this is even the mean strength is higher than the mean stress. Still, there's a probability of a failure when this kind of a weaker unit is facing higher than average stress, then you have a probability of failure. But you can make the system more robust by changing that direction or that into this direction. Okay, so this should be quite obvious. If we are kind of talking about single stress and single strength. So in fact, what we were talking about were so-called threshold stress failure, meaning that death comes with a single bullet. So when stress exceeds the strength, then we have a failure. It's like in the case of my previous ceramic capacitor example, when the voltage over the electrodes increases the strength of the insulating or dielectric material, then the smoke comes out. But we have also other types of failures. Another one which is relatively straightforward is the cumulative stress failure. So let's come back to this stupid pen example. So if I just start increasing the stress, then we exceed the strength and it's failure. But also, if we would do a cumulative stressing. So for my polymer material, this is not very good example because polymers are typically not that sensitive to fatigue. But in principle, if I do this repetitive bendings long enough, also this pen would fail. So that's when you have your stresses below the strength, but you have high number of those, then you end up in a failure. And for example, electromigration is quite nice example here, which we come back. We start with this one, our third part of the course. So when you have an electric connector, like aluminum or copper connector, you put current through it, then the atoms in the conductor, sorry, if your current density is high enough, the atoms start to move, diffuse along with the electron flux. And sooner or later, that causes a failure. So that's a cumulative stress failure. It takes cycles or hours or something like that to fail. And then we have a combination. So combined threshold cumulative stress failure, meaning that certain stress makes your product weak against another stress. So let's say that back to the pen example. First, I'm doing the whole semester, every lecture, I'm bending my pen because I'm nervous. So during the semester, I'm doing this 10,000 times. Still, the pen does not fail. But then when I'm starting a new course in the fall, in the spring, I will bend once a little bit more. So I would use the same amount of stress what I have used now, of what I'm using now, but I have before that I have done 10,000 times like this. So I have initiated cracks here or defects, and then the strength of this pen has decreased during my cyclic loading, and then after that it fails with that, let's say, mechanical shock loading. So maybe that's not the best example, but let's say some other example could be that a corrosion or some electrochemical thing is affecting on your sample. So you have a, let's say, carbon steel bar. You put it outside, it gets rusty. So the iron reacts with humidity, forms a rust at the surface, and then you start bending it so it withstands less stress when it's rusty than when it was new. Or you leave, maybe a pen example, you leave this one, or I leave it outside. So there's a UV radiation, and the polymer is very sensitive against UV radiation because the UV cuts these bonds between the polymer chains. And when this pen stays outside in the sunlight for several weeks, it gets weaker against mechanical loading. Okay, so maybe again, self-evident thing. A materials engineer would define it like this. So stress intensity factor, the stress in the product and the defect, if that exceeds the let's say stress ductility, which is the material constant, then you have a fracture. Okay, let's not go into more details on that because that's just a way to describe that if you have either growth of defects or increase in the stresses, then the combination of this leads into exceeding the fracture ductility of a material, and that then cause a failure. maybe one more example here. You have your glass window. You apply certain stress to your glass. It's not failing because glass is really strong, but glass also has quite low fracture toughness, means that if you have a minor scratch in the glass, then you need much smaller force to break it. Now this is used when we want to cut glass into smaller pieces. We use the diamond pen and then we bend it and then it cracks. Okay, let's go forward. Where do electronics fail? So maybe it's not even electronics. Where do whatever product fail? It's typically some kind of a translational area. So a location where something is changing. It can be geometry. Let's say you have a corner like here. This is a microwire from a printed wiring board. So you can see that here the failures have occurred in these sharp corners, because when you apply bending, or in this case it was mechanical shock loading, which caused large bendings, then this is the weakest link. You think that if you push this one part upwards and these are fixed, then it starts to bend, and this is the weakest link. Quite often different types of corners or something like that, they are critical. Here is a plated through hole solder joint. So this is printed wiring board, component lead. This is our solder material. So the failures are propagated here because of the geometrical reasons. And then quite often, sorry, it is because of material transition. So it's an interface, like here. This failure is between the ceramic material and the metallic contact metallization, so the failure has propagated here. So we can have zillions of examples of this kind of thing, that very rarely the actual failure is going through a bulk material, or so it's always some kind of a translational interfacial somewhere where there's a change in either in geometry or in materials. Okay, and now we kind of conclude our stress versus strength approach, and here now we have the same strength and stress distribution. Now it's just flipped 90 degrees, and here on the x-axis we have time. What means is that now we assume that the stress distribution stays constant. So basically, I am using my phone today as well as after 3 years with the same way. So the stresses are constant, but the strength is decreasing because there are these stresses, either this stress or some other stress is decreasing the mean or average strength. So this dashed line here describes how the average or mean strength is decreased as a function of time. And then after a certain amount of time, then the probability of failure starts to increase when these distributions meet. So this basically defines the lifetime or the time when the wear out starts. So here we are talking about random failures, overstress failures, and here then after a certain time we are talking about wear out failures. So this is how we link this stress strength analysis to bathtub curve, which we will be seeing in a minute. Few more questions. How do materials get old? So what is the effect of aging? And here quite often we are kind of going into the area of material science. So what kind of microstructural or structural changes is happening during the usage under certain stresses? So here is an example again from our own experiment. So what you have in the upper row here is a solder interconnection. So this could be the BGA ball, which you saw in the first lecture. So component here, printed wiring board here, and the solder interconnections. So this is how the solder ball looks like after manufacturing. So this is called as solidified structure. You have there certain microstructure which is dependent on the process, the actual original chemical composition of the solder, and so on. But then after aging, in this case, the aging was thermal cycling. So this structure was cycled between -40 and +125 degrees centigrade. And after 1000 cycles, which in this case was about 41 days, so a little bit more than 1 month, then what is happening is that cracks are growing, but not only that the cracks are growing, also the actual microstructure is completely changing, meaning that the solder, the strength of the solder has decreased drastically. So here it's strong but less ductile, and here is more ductile but less strong, because the microstructure has changed. So let's not go into the details here. We can, if we have time at the, let's say, last lecture of this course, we can go a little bit deeper what is happening here. But the point is just that when the sample has just come out from the furnace, it has certain properties, and then when you start using it, it starts to get old, and it does not anymore withstand the same stresses as when it was new. And this is especially true for the let's say materials which are low temperature. Was there a question or?
Yeah, can I ask a question about this?
Of course,
sorry.
please do.
So I was wondering if it's really only the strength that deteriorates. Like looking at the second picture, I would also guess that the conductivity decreases and the resistance goes up of the solder bond. Is that true, or?
Yeah, so it's of course dependent on the what are the stresses what we are imposing. So in this case, this was just, let's say, dummy thermal cycling. So there was no electricity going through this pump. Of course, very small current so that one can monitor if the pump is still working or not. But if we would think about actual, let's say, product, and we would put some current through here, naturally, when the cross-sectional area is decreasing, then the resistance is increasing. So basically what it does is it causes Joule heating, meaning that the local temperature would be increased. So it would be kind of cumulative effect for thermal cycling.
It's snowballing, right?
Yes.
Okay.
Yeah, it's kind of a snowball effect. And for, let's say, if you think about the most components in your mobile phone, this would not be a problem because the current densities are quite small. But let's say the processor component or some power controllers might have locally a little bit higher temperatures because of power losses. If we are going, for example, to automotive or especially industrial electronics, there the local current densities can be really high, so you have lots of power losses. Also, of course, in electrical vehicles and so on. Anywhere where you need high power components, then this would be much more severe problem. But this was a good point that of course we need to consider also the stresses, which really there is.
Thanks.
Okay. Yeah. Good. Thanks for the question. Then one more thing is that still looking at basically the same structure, and now with this picture, I want to highlight that how does the stress itself affect, and here the point is the strain rate. This might be a little bit difficult to understand if you don't have any background in the material science, but basically some materials are more sensitive to strain rate than the others. It means that the material behaves differently if you apply the same typically mechanical stress either slowly or rapidly. It means that if this would be a metal pen and it would be very strain rate sensitive material, if I'm bending it very slowly, it might withstand the same amount of displacement. But if I do the bending very rapidly, then it could break. So, for example, this example is coming from shock loading conditions. So if we cause the same bending by changing the temperature, meaning the same stress conditions what was in the previous slide, so that the materials are expanding, the printed wiring board expands more than the component, it causes bending and shear stresses. But on the other hand, if we have the same structure and we drop our phone to the floor, then the same bending occurs in the millisecond range. And then the failure is completely different. So here in the left-hand side upper corner, we end up having this kind of a fatigue failure, which means that the most vulnerable material in the interconnection is the actual solder. So we get this kind of a fatigue failure. Every cycle, the crack grows a little bit and so on. The stresses are distributed over the actual solder joint, and here what we have done is just put that in this case the maximum stress what we can find is just one, whatever unit. So it's kind of normalized stress. If we apply the same bending, so exactly the same amount of bending, but we apply that one with 1 million times faster. So here the strain rate is 0.001% per second, meaning that we increase the length of a certain material so that it is increased with the rate of 0.01% per second. So it takes 1,000, let's say 100,000 seconds to increase the length to 100%, so double the length. So this is typical for normal thermal cycling conditions. And now if we increase the strain rate, so 100 times faster, another 100 times faster, another 100 times faster. So now we have a strain rate of 1,000% per second, meaning that it's 10 per second. So in 1 second, the dimension is increased 10 times. So it's originally 1 millimeter, then in 1 second, it is stretched to 1 centimeter. So that is just the point. Then we see that the stresses are much more concentrated and the absolute amount of stress is also much higher, 1,600 times higher. And then the failure is also completely different. So the weakest link is not the actual solder, but the interface between the solder and the metallization. So this just points out that if we are designing the solder joint against thermal cycling, we need to pay attention to the properties of the solder joint. But if we are designing the solder joint against shock loading, dropping conditions, then we need to pay more attention on the interface between the solder and the metallization. So actually the intermetallic compounds, the chemical reaction products which are happening. So this might be a little bit confusing now, but also here we can come back in the final parts of the course. But the point is just that especially in the mechanical loading, there's a huge difference how fast we apply the load, because materials are sensitive to rate of the load. So strain rate dependency is the correct definition. Okay, now we have still 15 minutes time, so let's discuss shortly about bathtub curve. So also this is I would say relatively extremely simple thing, but what now I want to emphasize is that how you can utilize this bathtub curve in order to, let's say, understand the different phases in the life cycle and also correlate the stress versus strength approach to bathtub curve. So bathtub curve is, well, what do we have? We have in the y-axis, we have failure rate, meaning that how many failures per unit time, and in x-axis we have the time. And let's say sometimes this bathtub curve is also used to describe the maturity of the design, meaning that if you are manufacturing something today, you have high failure rate, and then when the maturity increases, so you get rid of all the manufacturing related challenges, then the failure rate decreases. I don't think this is a good way to use bathtub curve, because then this increase is rather difficult to kind of explain why, if you have manufactured something for 20 years, then again the failure rate is increased. So let's not use even that. Sometimes in the literature you can also see this kind of interpretation. Let's not use that one in this course. Here we more consider that this is the probability of a failure of a component as a function of its lifetime. Here it's manufactured, and then the probability is first high, then constant, and then it starts to increase again. So this describes the kind of three phases in the lifetime of an average component or system. So again, one needs to kind of understand that this is not for one single component. It's on average, if you have 1 million components, then they behave like this. So in fact, I think I added there in my courses one at least article on kind of critical look for bathtub curve. So actually nobody really knows who invented bathtub curve. Every reliability engineering handbook has it, but never we have an actual reference that, okay, this was the guy, John Bathtub, who developed it, or whoever. So it's kind of not clear where it's coming from. And in fact, we don't have any empirical evidence that this would be a real thing. So nobody has really never proved that this kind of behavior exists. But still, that doesn't mean that this is complete crap. Sorry, this bathtub curve. It's very good in design for reliability, for way of thinking. But let's not consider it as an absolute truth for something. I will next lecture, or maybe next Tuesday, I will show you some data, which is in Tummala's book, which kind of shows bathtub curve, but maybe we can then afterwards a little bit think if we accept that or not. But anyway, the point is that this is a model which describes, let's say, large number of components and or whatever parts and their average behavior. It is not for a, let's say, single component or single assembly or single system, but on average, large number of those. So we have basically the bathtub curve is composed of 3 independent curves. So we have the decreasing failure rate, we have the constant failure rate, and we have the increasing failure rate. And then when you sum up these, then you end up having this kind of bathtub shape. So let's check these 3 separate parts. So first, the first part, so the decreasing failure rate, and that is typically referred to Monday morning products, infant mortality. So those units which have some quality-related defects. So the reason behind might be, let's say, improper, inadequate quality control, uncontrolled manufacturing processes. During the testing, you go outside the specifications. You have some design or material failures. You have some improper handling of packaging, meaning that you put your thumb on somewhere and there's salt and grease, and then during the transportation you get some humidity, and then your contact surfaces start to corrode or whatever. So these are basically some kind of mistakes that somebody is doing, either in the design table or in the actual manufacturing or testing. And this kind of leads into a situation that in addition to your main population, you also have weak population, which means that we can go back to the strength approach. So now here we have the stresses, and here we have the main population where the average strength is way higher than the average stress. So basically, we do not expect failures, random failures, but we have a weak population here, where the average or mean strength of this weak population is really clearly below the average or mean of the stress. So it means that these products have some hidden defects and they will die immediately or very early in their lifetime. And of course, this is something that we want to avoid. So first of all, we want to avoid the production of these, but we also want to avoid that these are not entering to the customer. So we want to find these, and stress screening is used for that. So we'll come back to that in the second part of the course. So infant mortality, decreasing failure rate is the first part of the bathtub curve. Then we have the so-called random failures or overstress failures. So this is the part, the center part of the bathtub curve, and now this the level is defined by this acceptable failure levels. So again, if we come back to the question in the beginning of the lecture, what is the acceptable failure level for an airbag? And that is extremely small. Even one airbag fails during the 10 years operation of the car, that causes severe problems to the manufacturer. So we need to push these overstress failures as small as possible. So this comes back now to the robustness of the system. So if we have again here the stress versus strength analysis, this is the big population, we get rid of that one, but then we have here, if the main population, the average strength is quite close to the average stress, then, and the distribution is relatively large, then we always have this area here where the stress exceeds the strength, and basically this part here defines the failure rate in the center part of the bathtub curve. And then the third part is the wear out. So this is what we are mainly interested in our course. So how can we understand when the failure rate again starts to increase, because that defines the useful lifetime of the product. So quite often there is some kind of a physical mechanisms behind. So it could be corrosion, it could be mechanical stresses, it could be electrical stresses, it could be UV radiation, it could be moisture absorption, whatever, which starts to deteriorate the strength of the material, and then even the stresses are constant, then the probability of the failure starts to increase. So we end up having bathtub curve shape, infant mortality, constant failure rate, and then wear out. And now this just a little bit strange looking curve, but the point here is just to show that if you have a standard component board, meaning that you have the printed wiring board, you have certain amount of components, and you have these components soldered on the board, typically the components dominate the infant mortality. So the actual solder joints, they do not fail early if you don't have some severe manufacturing problems. So the components themselves, the component quality is dominating the infant mortality. Then the wear out part is typically dominated by the solder interconnections, because they are getting old, as was described earlier. So when you use them, then the microstructure is evolving, they are becoming more sensitive to mechanical loads, and depending on the structure here, these two curves, this is if the components have leads and if the component is leadless. Then if it's leadless, the stresses are higher, then it starts to wear out earlier than if the component has leads, it starts wear out later. So now for user or customer, we see kind of the combined effect of all these. So in fact, the bathtub curve is kind of containing several different failure modes. Some of the failure modes dominate in the early part of the lifetime. Some of them are dominating at the normal useful life, and then some of them are dominating at the end of the life. And this is behavior we can also describe with statistical mathematics, and there this Weibull distribution, Weibull statistics is the most commonly used. So because in Weibull you have two different parameters, the characteristic drive time, but also the shape parameter. And the shape parameter, this beta here, is describing in which stage we are at the bathtub curve. So when beta is 1, then we are here. If beta is below 1, we are here. And if beta is above 1, we are here. So if this sounds strange, no worries, because we are coming back to this one. And you can find this data in every reliability handbook. Okay, it seems that again the time is up, so we were able to cover the most important things. So just to highlight, stress versus strength approach, and then fast-up curve, and how these two are interlinked. That was the main point for today's lecture. And then what I would still want to say, the last word is that please join next week, and sorry, not next week, next Thursday. So on Thursday, I will introduce the failure mode and effect analysis, and I will give you the instructions for the first assignment. And that is really the larger assignment. You need to put quite a lot of time on that. So I think I, of course, try to also give very good written instructions, but always it's best to join in, ask if you don't understand what are the requirements, what you need to do. So let's see on Thursday and continue from here. Okay, I'm still free. I will now stop the recording.